Hi, my name is dr. Ahmath. Welcome to the course of Probability and Statistics. In this lecture, we're going to continue our discussions about the testing the hypothesis. And this lecture is going to be more practical. We are going to solve a couple of problems and understand the things with more details. And at the same time, we're going to introduce the steps in the algorithm of testing the hypothesis in general case. And we're going to introduce a couple of more concepts like rejection regions and the critical points. So in this lecture, we are going to solve the problems mostly about the testing the hypothesis, about the population mean in the different situations. So first thing which we are going to do is we're going to go through the steps which we have to perform in order to test the hypothesis. So the very first thing which we have to do is to write down the claim mathematically. So we need to write down the null hypothesis and the alternative hypothesis for the claim. And the step number two, in order to test the claim, we have to take a sample and calculate the test statistic. Step number three is identifying the type of the test and calculating the p-value. So depending on the sign of the alternative hypothesis, we are going to choose the different test types. So if the sign of the alternative hypothesis is the less sign, then we're going to use the left tail test. If the sign of the alternative hypothesis is the greater sign, then we're going to use the right test. Non-equality sign of the alternative hypothesis means that we have to use the T-tail test. So depending on the test type, we are going to choose the different areas under the standard normal distribution curve as the p-value, where the p-value is the numerical value which represents the plausibility of the null hypothesis. It basically tells me how much the null hypothesis is probable. So the greater p-value means that the null hypothesis is more probable. So once you've calculated the p-value by calculating the area, for example, for the right tail test, you're going to calculate this area. What you have to do is you need to decide whether this p-value is significant enough for you or not. For example, you've calculated the p-value is equal to the 0.05, for example, and you need to decide whether this is good. Is it significantly big enough for you or not? So usually you will be given a threshold. So so if the p-value is greater than this, then the null hypothesis is significantly plausible. If this is smaller than this threshold, then no, it is not significantly enough to be probable. But this threshold is defined so standardly this threshold might be 1%, 5%, or 10%, but you have to define this depending on the context of the problem. So basically, if the p-value is greater than the threshold, greater than the smallest value, it means that the plausibility of your null hypothesis is significant. So the null hypothesis is true. So we're not going to fail the null hypothesis. If the p-value is smaller, even this level of significance, then we are going to fail the null hypothesis. But the thing is, in the step number 4, we are making the conclusions about the null hypothesis. And if your claim is the alternative hypothesis, you need to make the conclusions properly. So let's assume that your claim might be the null hypothesis or the alternative hypothesis. And the step number 4 tells you your conclusion about the null hypothesis. If it tells you that you have to reject the null hypothesis, then you are going to reject your claim if it is the null hypothesis. You're not going to reject. You're going to support the claim if it is the alternative hypothesis. But if the step number 4 tells you that you are not going to reject the null hypothesis, then you're not going to reject the claim if it is null hypothesis, but at the same time, you're not going to support the claim if it is alternative hypothesis. So the step number 5 might be slightly confusing, but like memorizing the structure is very helpful. So what we are going to do is we are going to go through all of the steps whenever we are going to test the hypothesis about the population mean, proportion, or the variance. And the only difference is the only thing which is not so clear for me at this stage is how to calculate the test statistic. So depending on what we're testing, the mean, proportion, or the variance, this test statistic is calculation. The test statistic is going to be different. So essentially, all the steps are going to be the same. So the only difference is going to be calculating the test statistic. So what's the test statistic actually? So whenever we're testing the hypothesis about the population parameter, what we're going to do is, for example, the mean, right? So the mu is the population parameter. We're going to take a sample, calculate its proper test statistic or statistic, which is going to be the mean of a sample. The thing is, we are going to calculate, so the thing is, the central limit theorem tells us that the mean of a sample has a normal distribution, but we don't need a normal distribution. We need even more. We need the standard normal distribution. So in order to be able to use the standard normal distribution, we need to standardize the test statistic as well. So that is why in our calculations, we're going to use the standardized test statistic, which is going to be calculated using this formula. Then just using the standardized test statistic, we're going to make our conclusions about the population parameter. So let's do an example. So a manufacturer claims that its rechargeable batteries are good for an average more than 1,000 charges. So this is the claim of the manufacturer. Probably he doesn't know, or she doesn't know about all of the batteries which they produce, because they might produce millions of batteries. So we would like to test this claim. In order to test this claim, what we did is we took a small sample of 100 batteries and we tested every single battery on the average lifetime. So for example, we've got the 100 batteries. The first battery has been working for 1,015 times. The second battery 989 times, and so on. We tested all the 100 batteries, so 1,002, let's say. Then we've got the mean of all of these batteries, which is good. So all of these average lifetimes, it is going to be equal to the 1,002. And here the standard deviation 14 is given not for the sample, it is given for the population proportion. So what we need to do in this problem is we need to check this claim at the level of significance 1%. In order to test this claim, we are going to perform all of the 5 steps which we have introduced in the first slide. So the step number 1 is we need to write down the claim mathematically. So the claim tells you that the average lifetime is more than 1,000. So this is our claim. And if you look to the sign of the claim, it's a greater sign. It means that this is the alternative hypothesis. So the alternative hypothesis is mu is more than 1,000. So always we need to define the both of the hypothesis, the alternative hypothesis and the null hypothesis. So the null hypothesis is going to be the complement of the alternative hypothesis, or the opposite to the alternative hypothesis. It's going to be mu is less or equal to the 1,000. So in step number 2, we have to calculate the test statistic, right? So we are testing the hypothesis about the mean. So that is why the test statistic, or the standardized test statistic, is going to be calculated using the following formula. So the x bar minus mu divided to the sigma divided to the square root of 10. Or sorry, so square root of 100. We are going to just put all the numbers here. So we are given the x bar, which is going to be mean of the sample, which is 1,002. Minus mean, which is going to be 1,000, divided to the sigma, which is 14, and this is also divided to the square root of 100, which is 10 actually. So this is going to be 2 divided to the 14 multiplied to the 10, which is going to be roughly equal to the 143. Okay, so this is the test statistic. So in step number 3, we have to identify the test type and calculate the p-value. So in order to identify the test type, we need to look to the alternative hypothesis always. So the sign of the alternative hypothesis is going to tell us what type of the test we are going to use. So here, the sign of the alternative hypothesis is the greater sign, right? So it means that we need to use the right tail area as the p-value. So in order to calculate the p-value, we need actually the standard Z distribution table. So here, we've just calculated that we need to use the right tail test. So this Z is going to be equal to the 1.43, right? So this is our Z we've just calculated. And we have to take this area since the sign of the alternative hypothesis. The alternative hypothesis is actually equal, tells you mu is more than 1,000, right? This is the alternative hypothesis. It tells you that the mu is more than 1,000, so that is why we need to take the right tail area. So in order to do this, we need to use this table. So this table is going to tell us the areas until that Z, which is measured from the left. So from this table, I can find that the area until 1.43 is going to be equal to the 0.9236. So this area is actually this one. the more left area. So this is going to be equal to the 9,236. So, but we need this area. So this is our p-value, right? So in order to find this p-value, we have to subtract 0.9236 from the 1, since the overall area under the standard normal distribution curve should be equal to the 1. It's going to be 1 minus 0.9236. It's going to be equal to 0.0764. Or, sorry, you probably don't see this. So if you subtract this, it's going to be equal to the p-value is going to be equal to 1 minus 0.9236, which is going to be equal to 0.0764. So this is our p-value. We need to go to the step number 4 and compare the p-value with the level of significance. So previously in the step number 4, so the p-value is equal to 0.0764, right? And we have to compare this with the level of significance alpha, which is going to be 0.01. So is it bigger than alpha? Yes, it means that our null hypothesis is significant enough in order to accept this. We're not going to reject the null hypothesis. So the null hypothesis is not rejected. But if you remember, our claim is the alternative hypothesis, right? Alternative hypothesis. So we cannot say that we're not going to reject the claim because our claim is not the null hypothesis. So since our claim is the alternative hypothesis, we are going to do the opposite to the step, right? We're not going to support this. So we usually say that the conclusion in the full way, it's going to be like at the level of significance 1%, 0.01, there is not enough evidence to support the claim. So this is how the proper conclusion about the hypothesis should look like. So the thing is, we need to, so what we did right now is we drew this normal distribution curve, and we found out the test statistic, we calculated the test statistic, and we found the area which is more right using this table. And calculating this always, okay, so the calculations are not so difficult, but we always need the Z table in order to calculate the p-value. For example, if the Z is equal to the 1.56, then we have to take a table and calculate this. If the Z is equal to the 1.96, then we have to take a table and calculate this. But actually, we don't need this we don't need actually the exact area, the p-value. So what we're doing, the next step is we are comparing this p-value with the level of significance, right? So the level of significance in this case is also another area on the right tail test, on the right tail, right? So we are comparing this blue area with the red area. So the idea of do not calculate it, so knowing this without calculating the areas would be to just calculate the Z which corresponds to this red area. So if you know, for example, that your p-value, as in our previous example, is equal to 0.0706 or 64 or something this, so this Z was equal to the 1.43, right? And we've calculated the rejection regions, or the alpha level of significance was given as so let's say 0.1, okay? So if you are given the alpha, the level of significance, we are always comparing this p-value with this one, right? So what we did is we calculated first of all the Z. So now I'm telling you, hey, you don't need a p-value in order to know that your p-value is going to be smaller than alpha. So in order to do this, it appears, you just need to know which value corresponds to this area 0.1. So this Z value we are going to call as the critical point. So basically, we have to just compare this z with this one. If this critical value, if our z, the test statistic, is more than the critical value, it means that obviously the area which is more brighter, this blue area, obviously is going to be smaller than alpha, and we're going to reject this, right? So every z which is going to be more brighter than this critical value is going to be in the rejection region. So we call this region as a rejection region because every z value which is going to be more brighter than the critical value is going to have the p-value which is going to be smaller than alpha. So this is called the rejection region, and we're going to use the rejection region mostly in order to test the hypothesis, because in this case we don't need to calculate the p-value for every single test statistic. What we have to do is we need to always calculate the test statistic and compare this with the critical value. So obviously, we have to calculate the critical value depending on the alpha as well, but usually those are the standard values, and it is more or less easy for us to calculate it. So let's discuss how we are going to do this in the example. So again, a local telephone company claims that the average length of the phone calls is equal to the 8 minutes. So in a random sample of 58 calls, the sample mean is equal to the 7.8, and the standard deviation of the population is equal to the 0.5. So we have to test this claim at the level of significance 5%. So again, what we are going to do is, so we need to write down, first of all, what is our claim. So our claim is the mean is equal to the 8 minutes. So the mean of the phone calls is equal to the 8 minutes, right? So what I see here is equality sign. It means that this is the null hypothesis. So the null hypothesis is the mean is equal to the 8. So the alternative hypothesis is going to be the complement, or the opposite to the null hypothesis. The alternative hypothesis is going to be mean is not equal to the 8. So this is the step number 1. And the step number 2, what we have to do is we need to calculate the standardized test statistic, right? So this is going to be z0, which is going to be equal to the x bar minus mu divided to the sigma divided to the square root of n. Square root of n. So let's calculate this. So the x bar here is the samples mean. So samples mean is equal to the 7.8 minutes minus the mean of a population is given in the hypothesis is going to be 8 divided to the standard deviation of the population, which is somehow known, and it's given to be equal to the 0.5, and this is divided to the square root of n, which is going to be square root of 58, which is the sample size, right? That is given to here. So we can calculate this. It's going to be minus 0.2 divided to the 0.5 times square root of 58. So let me calculate this. If you calculate this, it is going to be minus 3.05. So minus 3.05. This is the test statistic. So previously, what we did is we found this minus 0.05, and we found out the p-values, right, using the table. So in this case, we're going to do this a little bit differently. So now, first, in the step number 3, what we have to do is we need to identify the test type, right? So the test type is identified by looking to the sign of the alternative hypothesis here. So the sign of the alternative hypothesis is non-equality sign. It means that the test type is the two-tail. So two-tail test, it means that the areas on the balls of the tails are going to tell us the p-value. So what we're going to do is slide it in this way. So we need to draw this. So the level of significance, 5%. 0.05. It means that this area plus this area in the sum should give you 0.05, right? So this area here at the stage is going to be half of the alpha, right? Alpha over 2, or 0.025. And this area should be also half of this. It is going to be 0.025. So if you find this, it's going to be, okay, so this value from the table is going to be minus 1.96. and this area, this value is going to be plus 1.96. So you can find this from the table. So what we need to do is, now we are not going to calculate the p-value. What we need to do is we need to just place onto this map the value of the standardized test statistic, which we have just calculated. So the value of the standardized test is roughly here, right? Which was minus 3.05, right? So which is actually on the rejection region. If you even calculate the p-value, so this is going to be this area, and you have to put this here. So the p-value is going to be the sum of these two red areas. And obviously, the sum of these two red areas is going to be smaller than the sum of the white areas, right? So it means that we don't need to calculate the p-value. We just need to check whether our standardized test statistic is in the rejection region or not. If it is in the rejection region, obviously the p-value is going to be smaller than the significance level. So it means that we're going to fail the null hypothesis, or reject the null hypothesis, sorry. So next conclusions is that, so in the step number 4, roughly, right, we knew that the standardized test statistic is in the rejection region. So it means that the p-value is going to be smaller than the level of significance, right? It means that the null hypothesis is rejected. So the p-value, which is the plausibility of the null hypothesis, is not significantly big, and we cannot accept this. We are going to reject this. And the step number 5, we have to write down our proper conclusions. If you remember, our claim was the null hypothesis, right? It tells you that the mean is actually equal to the 8 minutes, which is the null hypothesis. So that is why we have to write this. At the level of significance, 5%, there is not enough evidence. Oh, there is enough evidence, sorry. Oh, let me just erase this. There is enough evidence to reject the claim, because we are going to reject this claim. Good. So the only thing which basically may bother me is that when we calculate the test statistic here is x bar minus mu divided to the sigma divided to the square root of n, right? So here the thing is, we know how to calculate the x bar, right? So we take a sample and calculate the mean of a sample. We know what is the mean, mu, because it is usually given. So we're testing the hypothesis about the mean, actually, right? And the only thing is, how do I know the sigma? So if it is given, then yes, I mean, usually in practice, the standard deviation of the population is not given. So what we can do is we can substitute the standard deviation of the population as a standard deviation of the sample. But in this case, we can't use the standard normal distribution curve anymore. We have to use the student's t-distribution. So if the sigma of the population, basically the standard deviation of the population, is not known, then we need to use the standard deviation of the sample. But in this case, we need to use the t-distribution. So in the t-distribution, our calculations is going to be more or less the same. So the test statistic is going to be essentially the same formula. The only problem is, in order to find the rejection regions, we need to use the t-table, not the z-table. So let's do an example one more time. So essentially, it's going to be the same problem. So the local company claims that the average phone calls is equal to the 8 minutes. We take a sample of 26 phone calls, calculate the mean, it is equal to the 7.8, and the standard deviation is equal to 0.5 minutes. So we need to test this claim at the level of significance 5%. So again, we are going to do our standard steps. So the null hypothesis is going to be mean is equal to the 8 minutes, and this is our claim. So the alternative hypothesis is going to be the opposite to the null, which is going to be mu is not equal to the 8. Step number 2 is we need to calculate the standardized test statistics. So in this case, we're going to call this as a t0, but the formula is going to be the same. It's going to be x bar minus mu divided now to the s, because we don't know what is the standard deviation of the population. We've calculated this from the sample, divided to the square root of n, and we have to calculate this. So it's going to be so minus 7.8, so plus 7.8 minus 8 divided to the 0.5 times square root of 26. It's going to be equal to minus 2 over 5, or which is going to be 0.4, right? So 2 over 5, 0.4 times square root of 26. So let me calculate this using the calculator. So 26 times 0.4. It's going to be 2.03. It's going to be 2.03, roughly. Okay, so now next step is we need to define the rejection regions, but now in order to define the rejection regions, we're going to use the T table, right? So in order to use the rejection, in order to find the rejection regions, what we need to know? We need to know the test type. So in order to do this, we need to look to the sign of the alternative hypothesis. Since that is non-equality sign, it means that the test type is a two-tailed test. We need to also know the n, the number of these, so the size of the sample, because we need to calculate the degrees of freedom. So the degrees of freedom is going to be n minus 1, the sample size minus 1. In this case, it's going to be 25. So, and also we need to know the level of significance, which is going to be 0.05. So let's go to the table and try to calculate this here. So this is the T table, so which is basically is going to be given depending on the degrees of freedom and the confidence level. Okay. So here you see, so it is given the confidence level. If you remember, the confidence level is the area in the middle, right? So if the alpha is given to be equal to the 0.05, right? The alpha actually, it's the area in both of the tails here, right? Because our test type is the two-tail test. If it would be just the right tail test, for example, or the left tail test, then its alpha would be just the area in one of the tails. So since this alpha is the area in both of the tails, what we have to do is we need to basically, so the C, the confidence level here is going to be 0.95. So that this area on this tail plus this area on this tail is going to be equal to the alpha, so that the sum is going to be equal to the 1. Okay, so now what we have to do is we need to know the degrees of freedom, and the level of confidence is 0.95, and this number is going to be equal to the 2.06. So the critical point is going to be equal to the 2.06, and this critical point is going to be minus 2.06. If you remember, we've just calculated the test statistic, so the test statistic was equal to the plus 2.03. So it's roughly on the border of the critical point of the rejection region, right? It's going to be 2.03, which is not in the rejection region, right? So it means that if you would calculate the p-value, which is going to be this area here, and you have to add this to this area as well, right? So then this red area would be greater than the white area. It means that the p-value, the plausibility of the null hypothesis, is significant enough for us to do not reject the null hypothesis. But it's enough to just place this standardized test statistic onto this map and see whether this is in the rejection region or not. So we are going to make the conclusion in this way. So step number 4 tells me that the p-value is greater than alpha. It means that the null hypothesis is not rejected, right? So if you remember, our claim is if you remember, our claim is also the null hypothesis. So it means that step number 5, the null hypothesis is not rejected, or a claim is also not rejected, so is not rejected. So that is why we usually write this at the level of significance 0.05. There is not enough evidence, reasons to reject the claim. So this is how we need to test the claim about the population mean, depending on whether you know the sigma, then you need to use the Z table, or you don't know the sigma, so the standard deviation of the population, then in this case, you need to use the T table. So in our next lectures, we're going to test the hypothesis about the population proportions and the variance. Thank you.